Welcome to the video on domains and ranges of polynomials, radical, rational, logarithmic, and exponential functions. Objectives: find the domain and range of polynomial functions, radical functions, rational functions, exponential functions, and logarithmic functions. About the polynomial p of x. The general formula for a polynomial is p of x equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus all the way until a sub 1 x to the power 1 plus a sub 0. A sub 0 is not associated with the variable x because x sub 0 is equal to 1. So this is a constant term. The rest of the terms are functions of x, and x is any real number. Also, every x has an exponent. The exponent is from the set of non-negative integers. Every term has a coefficient. The coefficient of the first term is a sub n, second term is a sub n minus 1, and so on. All the a's, a sub 1 and a sub 0 are all coefficients. The coefficients are from the set of real numbers as well. The value of n is considered to be the degree of the polynomial because n is the largest exponent, so the term with the largest exponent will be the dominant term, and it determines the behavior of the polynomial for large values of n. Polynomial doesn't have to have n plus 1 terms. Polynomial could have just one term or no terms. When the polynomial has no terms, it will be p of x equal to 0. When the polynomial has one term, it will be p of x equal to a sub n x to the power n. In this case, a sub n minus 1 is equal to 0 all the way until a sub 1 equal to 0 and a sub 0 equal to 0. Our focus will be for analyzing polynomials will be on a polynomial with a single term, just p of x equal to a sub n x to the power n. The reason being, it will simplify calculations because we need the calculations to prove all the hypotheses that we're going to set forth before we can start talking about the polynomials. So in general, let's take a look about the degree. Let's talk about the degree of the polynomial. The degree of the polynomial equals n for this case. This is the general formula. So its degree is n, the value of the highest exponent for all x's. The number of terms t of a polynomial can be from 0 to n plus 1. Like we said, a polynomial t could be greater or equal to 0. That means it includes 0. So if 0 means there is no term, all the coefficients are equal to 0, and p of x equal to 0. That's not an interesting polynomial. Our interest is a polynomial with degree 1, and that's what we will be handling throughout this discussion. An example of a polynomial is as follows: p of x equal to 4 pi x to the power 5 minus 1 half x to the power 4 minus 3 e to the power 8 x squared plus square root of 7 x plus 9. What is interesting is the following. We start from the first term here, 4 multiplied by pi multiplied by x to the power 5. So there is multiplication. There is exponentiation, x to the power 5. We have minus half x to the power 4. So there is subtraction. Half implies we're going to divide this term by 2. We divide x squared by 2. That means there is division. We have minus 3 e to the power x. That means we're involving exponentials in the coefficient. And then we have multiplication. We have plus, that means there is multiplication, there is addition. We have square root, there is square root. In general, a polynomial pretty much have all the common operators for arithmetic calculation. You can do multiplication, exponentiation, you can do difference, you can do division, you can do multiplication by exponential values, you can do addition, you can do square root. Also, let's just try to relate it to the general formula. So this is a polynomial of degree n equal to 5, and a sub 5 is equal to 4 pi. A sub 5 is equal to 4 pi. A sub 4 is equal to negative half. A sub 3 is equal to 0. That's why there is no x to the power 3 term. A sub 2 is equal to 3 e to the power 8. A sub 1 is equal to square root of 7, and a sub 0 equal to 9. So the polynomial, the domain of a polynomial is the set that feeds the polynomial with input. So the domain of a polynomial is the set of real numbers. That's from negative infinity to positive infinity. The range of a polynomial is the set from negative infinity to positive infinity, or the set from m, which is the absolute minima of the polynomial, all the way to infinity, or it could be from negative infinity to capital M, which is the absolute maxima of the polynomial. We'll talk about them in a minute. Let's suppose that we have a value that we're going to evaluate the polynomial, and that value is equal to x1. So p of x1 equals to m, which is this m. We're going to be discussing this m. If we said p of x1 equal to m, then the point x1 comma m, the coordinate x1 and the y coordinate is m. Then the point x1 comma m is the point with the lowest y coordinate compared to the rest of the points on the graph of the polynomial p of x. Also, if p of x2 equals to capital M, then the point x2 comma capital M is the point with the highest y coordinate compared to the rest of the points on the graph of the polynomial. Preface. To set up the stage for discussing the domain and range of a polynomial, let us, number one, introduce the input, process, output model for a polynomial. Number two, identify the domain of a polynomial and its relationship with the set of real numbers. Number three, prove the mapping process of a polynomial is 1-to-1. Use n, the degree of the polynomial, when it is an odd number to select its range among the three possible values. Use the sign of the polynomial's term with the highest x exponent when n is an even number to select the range. The input, process, output model for a polynomial. A polynomial have a set which is called domain, from which it receives its input. The inputs are values that are passed to the variable x, which is the independent variable. And now we have a representation of the domain of the polynomial. We chose the numbers from -4 all the way until +4, and we ordered them in increasing manner. Now, since the input, process, output receives the input from the polynomial, it passes it to the process, and then the process will produce an output, and the output will be passed to the range. So let's take a look at an example. Assume that the input is -4, so -4 will be passed, and it will be the value of x. So x is just put here as a model, but negative 4 is the only one that will be fed in. So negative 4 will be fed in, and then negative 4 will be where x is. So this is the value of x is negative 4. It will be raised to the power 3, and then the process will produce the output, which is p of negative 4. Once again, p of negative 4 just for explanation. But the output will be only negative 64. So negative 64 will be the output, but negative 64 will be passed to the set which is called the range, and this is the range, and this is negative 64 right there. In a way, we can say that the process will produce an element in the range based on an element in the domain. So if negative 4 was not there and was not passed, then we wouldn't have negative 64. And the same thing applies to negative 3, negative 2, all the way to all the elements. So if we compare the domain and the range, and if we think at the domain as a machine that for each of its members, it's going to produce a match here. It's going to produce element in the range such that that element is matched to one of the elements in the domain. So for the process produce negative 64 for negative 4. For negative 3, the process produce negative 27. For negative 2, the process produce negative 8, and so on. For positive 2, the process produced 8. So we can see for each and every element in the domain, there is a unique element that depends on the source element. Like for example, negative 64, it is cubic root will be 4. And 4, when raised to the power 3, it will be negative 64. So each and every element in the domain must be mapped to a unique element in the range. What does that tell us? That tells us that the number of elements, I'm just going to put number and then E for elements in the domain, which is just, I'm going to symbolize with D. It should be equal to the number of elements in the range. And I'm going to put R for range. So the number of elements in the domain must be equal to the number of elements in the range. Moreover, the mapping is clearly one-to-one. By one-to-one, we mean each element from the domain is mapped to a unique element in the range. And there is no element in the domain that is mapped to more than one element in the range. And the number of elements in the domain is exactly similar or equal to the number of elements in the range. Having said so, then we will use these two important conclusions. Number one, the mapping is one-to-one. Number two, the fact that the number of elements in the domain is the same as the number of elements in the range. So now we could go ahead and proceed with our discussion of the polynomial. Ranges of polynomials. Let's start with the polynomial of odd degree. Here is the degree, polynomial of odd degree. We know that the first row is a domain, and this is identical to the domain that we used for the IPO, and the range also is identical to the one we use for the IPO. We mentioned in the IPO that the mapping is one-to-one in the sense that every element in the domain is used to produce a matching element in the range, and the matching element is unique. Having stated so, then if the domain continues to increase to plus infinity, then so will the range will continue towards positive infinity. On the other hand, if the domain continues from the left to negative infinity, then the range will also continue to the left to negative infinity. Reason being, the mapping is one-to-one, and the cubic of every negative number is a negative number, So when the domain moves towards negative infinity, the range will also move towards negative infinity. The key is that the power of x is odd. So let's take a look at the case when the power of x is even. When the power of x is even, the process is the same. We take every element in the domain and the IPO will produce an element in the range, but the production is different here. All the negative values, they produce a positive value because the square of a negative value is a positive value. The impact of that is that if we looked from 0 to the right, we will see that the range will continue to increase. So if the domain increases to infinity, the range will also increase to infinity from this side. Let's take a look at to the left of the 0. To the left of the 0, we know that the domain will continue to decrease until it gets to negative infinity. However, the range will continue to increase in positive manner until it gets to positive infinity. So it will get to positive infinity. What does that mean? The degree is even and the coefficient is 1 because x squared means it 1 times x. So the coefficient is positive, and for that the lowest point for the range is 0. 0 is the lowest point for the range. Let's call it m. So m is the lowest point. The points to the right are more than m. 1, 4, 9, 16 all the way to infinity. And to the left 1, 4, 9, 16 all the way to infinity. So the lowest value is 0 and the highest value is infinity. So 0 we call it m. So m is included and the other side is not. So this is the range for a polynomial with even degree and also with a coefficient that is positive. That's it for this part. Let's continue analyzing the polynomial from a different. The range of a polynomial of the form p of x equal to a sub n x to the power n, that means a polynomial with one term. Its range will be from lowercase m to infinity, where lowercase m is the absolute minima. What is the condition for this? The condition is that n must be an even integer. N is the power of x, and a sub n must be a positive number. A sub n is the coefficient of x to the power n. Now let's go ahead and take a look at the table. This table is identical to the IPO that we spoke about. The domain of the IPO is the same as the domain we see over here, and the range is the same as the range we see over here, and the conclusions are also the same. That means for every element in the domain, the polynomial will produce an element in the range. That means as the domain grows towards infinity, the range will also grow towards infinity. So the range will grow towards infinity. Now let's take a look at the other side. On the other side, the domain continues to decrease until it goes to close to negative infinity. However, the range is not going to increase. The range is not going to decrease. The range will be increasing, and it's going to increase until it hits to positive infinity, towards positive infinity. To the right of the 0, the range is also increasing, and it will head towards positive infinity, as we said, positive infinity. So what is so special about the 0? There is one thing. The 0 is equal to m. Why? Because the 0 is the absolute minima. It is the absolute minima. Since 0 is the absolute minima, we can conclude that the range of the polynomial p of x equal to x squared is from m, which is absolute minima, and it included, because 0 is part of the range, all the way until positive infinity. So this is the range of the polynomial of degree n, which is even, the first condition, and of a coefficient, a positive coefficient, plus 1, which is the second condition. A sub n must be positive. So A sub 2 here is positive. So we were able to use the table to prove this hypothesis. Now let's go ahead and try to also prove this hypothesis using the graph of the polynomial. So let's get the graph of the polynomial and compare it. For the graph of the polynomial is the blue one. We have other graphs inside, but the most important thing is the fact that the graph of x squared is in the blue. So this is the graph of x squared. If we look at this point is equal to 0. Now, this point, if we go to the table, it is the smallest value compared to the rest of the range to the right and the rest of the range to the left. If we look over here, we have 0, so this is matching this 0. And then we have 1, so 1 is matching somewhere in here. And then we have 4, so 4 will probably be matching somewhere in here. And then we have 9, 9 will be matching somewhere in here. And 16, we cannot see it. So you can see that from 0 going to the right on the table is like from 0 climbing on the y direction towards infinity. And likewise on the left hand side also we will be climbing to the direction of y towards infinity. So if we want to know the range, then we know the range is the smallest value all the way until the largest value for y. And the smallest value for y is 0 here, and the largest value for y is infinity. 0 is included, so we'll put this, and this is infinity. But 0 is what is known as m. M is the absolute minima. So this 0 is the absolute minima because it is the smallest value on this curve. So it is m comma infinity. So this proves the case also using the graph of the function. Now we will go ahead and take the other situation. The range of a polynomial p of x equals to a sub n x to the power n. This is a polynomial with a single term. So n is the degree and a sub n is the coefficient. The range of such polynomial will be from negative infinity to capital M, where capital M is the absolute maxima on the graph of the polynomial. That is the point in the graph of the polynomial that has the largest value of y towards the y-axis. What is the condition for this? The condition is number 1, n should be an even integer. Number 2, a sub n should be a negative coefficient. So let's take a look at these two conditions. Here is a polynomial that we're trying to analyze, and for this polynomial we have n which is equal to 2 in this case, and 2 is an even integer, so this condition is satisfied. Number 2, a sub n is a negative number, where a sub n is a coefficient. What we see here is we have just the negative sign, so we have negative x squared. Negative x squared is equivalent to saying negative 1 multiplied by x squared. So negative 1 multiplied by x squared. That's what it is. So we can also say that the coefficient is a negative value. The coefficient is a negative value. And if that is the case, then we will try to prove that given these two are satisfied, then the range will be from this negative infinity to capital M. Let us focus on our center point. Our center point is always the 0. Since this particular polynomial is just the image of the polynomial that we used for p of x equal to x squared. I'm going to bring it over here. This is p of x equal to x squared. The only difference is this a sub n. A sub n is positive for this polynomial, but a sub n is negative for this polynomial. And for that reason, let's take a look at the members of the range. The members of the range all the way are positive. All the way are positive. And since we have negative sign before x, then the members over here all the way are negative. All the numbers are negative. So what does that mean? That means that from 0 to the right, it will continue to go to negative infinity, and from 0 to the left, it will also keep going from all the way to negative infinity. So what does that mean? That means our 0 is capital M. Our 0 is our absolute maxima, because every element to its left is less than it, and every element to its right is less than it. So that means this makes our 0 as capital M. Since we have this condition, which is even exponent and negative coefficient, we can prove now that the smallest value is negative infinity on both sides. So negative infinity, and the largest value is 0, because 0 is the largest value on this row. So the largest value is 0, and then 0 is included. But 0 represents capital M. So we are able to prove that the range for such, polynomial is from negative infinity to capital M, consistent with the hypothesis right here. Now, using the table, we're able to prove the hypothesis. Let's go ahead and use the graph of the polynomial. So let's get the graph of the polynomial and try to prove the same conclusion. So if we bring the graph in, we can see a few important things. I'm going to be quick. Number one is the 0 of the graph. This is the 0 of the graph. So this is the highest point on the graph of the polynomial. This polynomial is p of x equal to negative x squared. So the highest point is really 0, and every other point is negative, and they are continuing to decrease towards infinity from both sides. So what does that tell us? That tells us that the point 0 is actually the maxima. This is the maxima. So we can say that we have a maxima at 0 for this particular polynomial. Maxima, capital M, at 0. And also we know that the graph will continue to decrease towards negative values of y. It will be heading towards negative infinity, and from this side also it will continue to decrease on the negative side of y towards negative infinity. So if the largest value is 0, what is the smallest value? The smallest value is negative infinity. So we can say also that the range, which is along the y-axis, the range will be, the least value is this, and the highest value is 0. So we can say that the range is from negative infinity, the least, all the way to 0, which is the largest. So this we can compare it with the general formula, and the conclusion is that M, this M is 0 for this case. Our case, this is 0. The general formula is negative infinity and capital M. So for our case, capital M is equal to 0, which is right here. That's it. Let's go ahead and summarize these lessons. Summary. To summarize what we went through, we will ask questions and then answer them. First question: what is the domain of a polynomial? Answer: A polynomial can be expressed. We discussed the expression. A polynomial f of x will have input, which is called the parameter of the function or the polynomial, its input. The input to the polynomial is any number, can be any real number. And since the inputs to functions come from what's known as domain, and we said that the input to the polynomial is from the set of real numbers, then the domain of a polynomial is the set of real numbers. One more time. Since the input to functions come from what is known as the domain, the source of input to functions, and since the source of input to a polynomial is the set of real numbers, then the domain of the polynomial is the set of real numbers. That's the first part. Let's take a look at the second part. What is the range of a polynomial? Answer: if the degree of the polynomial is odd, then the range of the polynomial will be the set of real numbers, which is from negative infinity to infinity. However, if the degree is even, then the polynomial with a single term will have either a maxima or a minima. As such, the range will be from lowercase m included to infinity when the coefficient of x to the power n is positive. Otherwise, when the coefficient is negative, then the range will be from negative infinity to uppercase m. That's it, and thank you for watching. Stay healthy.